Thank you for joining and thank you for your time. My name is Anastasia and I'm working at MindSpider and I'm also a part of RECIRCULATE project. And we are happy to welcome you at the second Circle Battery Cluster webinar. So thank you for joining. And I will pass to Volker, my colleague. Volker is a co-founder and legal counsel at MindSpider, and he will be moderating our webinar today.
Yeah, hello everyone. Nice to meet you, and thank you, Anastasia, for the nice introduction. Yeah, first of all, as you saw, the topic that we want to discuss today and dive into a little bit deeper is automated versus manual, how robotics are transforming the battery inspection. And this is addressing a lot of different, very interesting issues and topics along the life cycle of a battery. Of course, inspection is a key element. And we have, I think, a very interesting list of speakers today. You saw them already in the invitation, but I will just just name them again, and then maybe later you introduce yourself. We have some presentations that you will see, and also even a video. And the idea is that the speakers give a little short introduction and then directly dive into the specific presentation or topic they want to address. Then we can have a short Q&A if needed, but at the end we will have a longer time for a longer Q&A. And so we have to keep the time, of course. And so we will check that everyone can follow. And if you have questions, maybe you in the chat also, you can mention them. And then we try to follow on the questions during this webinar already. If we think that things take more time to explain, then we will maybe have later per email or have a follow-up call if this is needed for you. But let's now just dive into it. So the speakers today will be, first of all, Dr. Tomi Pitkäaho. So he's the principal lecturer in research at Centria University. Then we will have Professor Rustam Stolkin, the chair of robotics at the University of Birmingham. And he's also the founder and director of the Extreme Robotics Lab. We will have visiting Professor Alireza Rastegapana. I hope I pronounced the name correct. He is lecturer at the Aston University and School of Computer Science and Digital Technologies. We have today Óscar Domínguez. He's a researcher and R&D and I project manager at Eurocad. And we have Giampiero Pupillo he's the automotive automation specialist at Comau. So I think maybe we start with the first speaker, with Tomi. Tomi, go ahead. It's your floor.
Great. Thank you very much, Volker. Yeah, so hello, everyone. Thank you for kind introduction, Volker. So my name is Tomi, as Volker mentioned, and I work at Centria University of Applied Sciences in Finland. Let me show my screen. Can you see it in the presentation mode? Great.
Yes, we see it well.
Perfect. Great, thanks a lot. Okay, so I'm going to talk a little bit about this project that Centria is coordinating at the moment. So it's a Horizon funded project. It's called RECIRCULATE, and we will have sister projects presented in this webinar as well. So it's really nice to see all of you here. So I'm going to talk a little bit what we have done in the RECIRCULATE project and what were the goals set at the beginning. And this project is ending at the end of next month, and so we have achieved some really nice results in this project. So we have partners also from Switzerland, outside EU. So there are two companies presented from Switzerland as well. So basically, the goal of this project was is to extend battery lifespan. So basically, when the EV batteries come to the end of their life, they can't be used anymore in the electric vehicles, but instead they can be used elsewhere. So basically, if you are extending the lifetime of those batteries, and in practice, what it means is the second life applications. So the project is built on the 6 pillars you can see here. So what we do in the project and what we have done is the SOX, state of X characterization. Then what we are focusing in this webinar is the automated dismantling based on AI. Obviously, we have used or have done also second life applications, so battery pack repair, reuse, and remanufacture. We have focused also for recycling, although the recycling is the last option that we really want to do. So what we want to do first of all is the second life, third life applications. We are focusing also for safe storage and transportation of the batteries and blockchain-based battery passport and marketplace. So at the bottom of the screen, you can see the partners in the project. So 11 partners across the Europe. Central University of Applied Sciences is coordinating this project. So we'll show a few-minute video in the next slide that should give you a better understanding what we have done in the project.
Uncommissioned EV batteries have multiple applications across different value chains. First, the battery pack is characterized by its state of health. State of health determines the pack's condition for second life applications. An ADR-compliant transportation unit is used for transportation. Module and cell temperature is constantly monitored during transportation, helping prevent thermal runaway. Battery packs with higher state of health can be utilized across different second life applications. Battery packs with lower state of health are transported to a disassembly facility. Beginning the disassembly, battery information is retrieved through a battery passport. The passport is accessible by scanning a QR code. Battery passport contains valuable information about battery chemistry, manufacturer, and disassembly. Disassembly is performed in a robotized environment. Robotized methods help mitigate risks of fire, electric shock, and physical strain, increasing safety and efficiency of the facility. Modules with lower state of health are selected for disassembly. Modules or individual cells can be used for different second life applications. An ADR-compliant transportation unit is used for transportation. Modules and cells are transported to second life usage or recycling facilities based on their condition. Modules with higher state of health can be utilized across different second life applications. Discarded cells and components are recycled by a battery recycling facility.
Okay, so that's basically like the overview of the whole project, what we have done in the past 3 years or so. But now we will focus on this robotics, disassembly, and how we have used robots for disassembly the batteries. So basically, this is the objective that we set at the beginning and preparation phase of the project. So we're going to build the AI-based automated dismantling and sorting system. And the KPIs that we set during the preparation phase was that we will identify the batteries with accuracy higher than 98% for 20 different battery types. And then we have the condition monitoring for visually classifying the condition of the batteries. So basically identifying different defects on the batteries, and that increases the process safety. So we set a goal of 10 different defect classes and classification accuracy over 99% of those. One of the KPIs we set at the beginning was that the pack to model disassembly takes less than 60 minutes, and then from model to cell less than 120 minutes, so 2 hours. This is the robot cell that was built during the project. So we have the KOKA KR10 industrial robot mounted on the linear unit. So it is working from up to down, so sort of upside down, so to extend the space where it can operate. And we have these different end effectors, so different robotic tools for the disassembly. So we're using pneumatic bolt gun at the moment for screw removal, vacuum gripper for the lid removal, for the radiator plate removal, and all the smooth surface lifting. We're using shank gripper, and we have 3D printed jaws for different operations, like removing the cables, removing the connectors. Then we have a custom designed gripper for modules and the BMS, so the same gripper can be used for both. And when we are doing the disassembly from modules to cells, we are using Dremel at the moment for cutting and milling tasks. In addition, we have 2 cameras in the robot cells, so we have two RealSense cameras there. So give it like an overview picture, and then one is on the robot flange. So basically, you can see this is the old camera that you can see in the figure. That has been replaced with the RealSense camera. But basically, it's a RGBD camera, 3D camera. The system relies strongly on machine learning, and we have multiple different machine learning models. The first one is the identifying the battery. So that eases the disassembly process. So if you can identify the battery, and we know that we have disassembled this before, so basically we can use the old approach, how we have disassembled the same type of battery before. Then we have the visual defect detection machine learning model that identifies those 10 different classes. An example of that you can see here on the top right-hand corner. So we can identify defects like classes, the punctures, dents, if there's a thermal damage of the battery, missing screws, missing components, and so on. And then we have a model for external components, so that identifies the screws, missing screws, and also the battery itself, so that we can use that information also in the digital twin of the system that was developed in the project. Then we have a different model for identifying the electric connectors inside the pack. We can also identify the wiring harness. We can segment that as well. And other components like modules, screws, and BMS, we have a different model for that. So in total, at the moment, we have 6 machine learning models for the disassembly. So please keep in mind that the first part, when we are disassembling from pack to module level, that relies strongly on machine learning. When we go from modules to cell level, that is a more traditional way. So that's where we use the fixtures. So we have a specific type. So we have the EV battery from Ford. So that's plug-in hybrid EV and the battery of that. And this project sort of built around that, and the proof of concept that we can do that disassembly is shown on these batteries. So this next two videos are both available in YouTube. So these are the official part of official deliverables delivered in the project. So this one, the first one here, so this shows the disassembly from pack to module level. So that starts by scanning the pack. So that's where we do the identification of the screws. And the screwdriver you can see here, this was actually replaced last autumn to a different one. But yeah, so the next step is to remove the screws, take off the lid, that gives us the access to the internal components. So this is where you can see the modules. So in this battery, you have 4 modules, and then the BMS here at the far end. Then we can identify the connectors. We can also identify from which direction we should approach the connectors based on the wires that we have there, so that it can be safely done. So there you can see the shunt gripper, and these are the 3D printed jaws that were designed and printed at Century. And then when we have removed all the connectors, the next step is to remove this wiring harness. And it is a really challenging task because it is so deformable. So it's really flexible, and it is hard for a robot to do this task. And you can see that we have changed the jaws for the gripper. So those were designed for this task to remove the wiring harness. And as you may know, and I'm sure most of you do, so one of the challenges we have is the adhesives, is the glue between the modules and the radiator plate. So what we have done there is that we are using liquid nitrogen to freeze the adhesive, so it sort of gets loose, and it is much easier to remove the modules from the radiator plate. And that's the radiator plate that you can see here at the bottom of the pack, below the modules. And then we remove the rest of the components here. So I'm going to jump on to this one. So basically this is the deliverable 2.4. So in this, we showed that we can go from modules to cell level. And this process is not relying strongly on the machine learning. So instead we have the fixture there. So the module is at the fixed position. So I'm going to jump here so that you can see the fixture. So it is at the fixed position. And this table was designed at Centria. So basically, if a thermal runaway happens, the model will drop down. So there's a water reservoir there below the table. One of the challenges here is that we have every 2 cells are welded together. So we have to remove these spot weldings there. So in this case, we used the Makita's spindle for removing those spot welds. And now in the current system, we are using Dremel instead of that spindle tool. and that's how we get the sales report. Okay, so at the moment we are in the phase where we are making the video of the final demonstrator, so that's going to be more optimized version than this one. So we have changed a bunch of the tools that we have used based on the experiments we have done. Besides that, we have implemented this digital twin of the system. That's what you can see here on the right-hand side. And we have used Unity game engine for that, and it is bidirectional, so it's an actual digital twin. So we can control the robot, and we can also get the robot information directly to the digital counterpart of the twin. And the same model, the digital model, was used also for reinforcement learning. That was used for investigation of if we can optimize the disassembly process through reinforcement learning. So as a conclusion, it's only 15 minutes was research. So as a conclusion, so what we have done is that we have shown the proof of concept, so we can do AI-based automated battery dismounting, and obviously this supports the EU's objective to scale recycling and reuse. And this kind of systems enables recycling. That's the last option in the RECIRCULATE project. So we are interested in second and third life applications. So these systems enables also second life industries to handle the expected surge in end-of-life batteries in cost-effective and safe manner. And this is where I end. So thank you for your attention.
Thank you, Tomi. That was really impressive, and I think it gave us a first, impression and understanding of how a robot, or what a robot can do, how you can automate things. In the next section, we will learn more about the comparison, manual versus automated battery inspection. But maybe one quick question, Tomi. What was the biggest challenge that you experienced from this?
Yes, so the biggest challenge at the moment is that the battery designs arise. So there's so many designs, and it is really challenging to come up with a solution that would work with every battery. And one of the technical challenges is obviously glue. It's the use of adhesives.
I see.
So those are the two major challenges that we have seen during the project.
Yeah, so I'm curious now what Rustam will show us and point to, because you dive deeper into this topic, right? So comparing manual versus automation, I think this is also quite interesting, and it will always change over time. But yeah, Rustam, maybe you can start and go ahead.
Yeah, thank you. I have to say, I thought that was extremely impressive, and so yeah, I'm not sure if I can live up to that, but I got some few interesting things. Let me try to share my screen.
Meanwhile, maybe I can also mention something that I experienced during the project. It was really impressive when you see something, how the robot starts learning things and how many difficulties it had at the beginning, and then when trying to grab something. But now I see your presentation. I think it works.
Yeah.
Maybe you go on full screen. Yeah, perfect. It looks good.
Can you hear me okay?
Yes, we hear you very well.
Yeah. Okay. So I think the overall Rebellion project, it has quite a similar structure as what was shown for RECIRCULATE. We have people working on how to safely transport the things in safety containers, and looking at what happens when things catch fire, and then other people looking at all different parts, and then people trying to make a second life product and these kind of things. Our lab at Birmingham, we're leading the automation and robotics work package, and there are a couple of other partners involved there. UPV, who's leading the overall Rebellion project, they also are doing some automation work. So they're looking at dismantling light vehicles like the batteries from electric bicycles and things like this. And I would say that compared to us, they are doing very practical thing at a very high TRL, whereas we're looking at maybe future-looking things that are a bit lower TRL. So the UPV guys, they have a process where part of the dismantling is done by hand with various tools and methods they've made. And then they also have a robot arm with a vision system that's picking up the extracted cells and putting them into testing machines. So it's a partially automated system, which it is quite constrained in a way that makes it quite applied and robust. And our work, and Ali Reza is co-PI with me on that work, and he's supervised a lot of the PhDs and things on this. So our work, we're looking more at sort of the cutting edge of autonomous and AI-assisted robotics research and seeing how those techniques could be applied to batteries in a very unconstrained situation. And like the previous speaker said, one of the big problems is that there's such a proliferation of these different types of these things, and how will a robot generalize? So we'll show something a bit more close to the research edge from robotics and see how we can try to make that relevant to this battery problem. And then Technical University of Košice, they're really fantastic mechanical engineers and mechatronic designers. So they're actually designing and building some really professional different types of tools to go on the robot for us, which my guys don't really have the capacity for that. They're more making the algorithms and the software. Yeah. So I'll give you a quick run through the sorts of things that we do. So we have something we call adaptive digital twin, but it's a bit more, it is kind of a software infrastructure that really joins all this stuff together, and it pulls in stuff from the vision system, but it links to the simulated robots for planning, and links to the real robots, and links to the cyber-physical human interfaces in various ways. So it permeates the work. So you can see there's quite some complex software infrastructure there to do all this stuff. And we can plan series of actions in the digital twin. We can pull in models of what's in the real world from our vision systems, and we can run the digital twin in parallel with the real robots. And bolted onto that digital twin, we've explored various kinds of human interfaces, and we thought some of these dismantling actions can be fully automated, but there will be some that are maybe too complex or too varied, where we will need some kind of human in the loop. And so we have various kinds of teleoperation at one end, full autonomy at the other, and various kinds of autonomy assisted human control in the middle, if that makes sense. So we've looked at a lot of different sort of VR, AR headsets. Here you can see Cesar's using, we've got two identical robots and using one as the master to control the other slave, which can be quite intuitive. We've also looked at a variety of different haptic devices. So in fact, what you can do is, what's happening here is Cesar is seeing what he would see if he was standing in the hazardous zone and looking at the slave robot and putting his hands on this robot and moving it to do what he wants. But he's seeing that through the goggles, but he's got his hands on a real robot that's identical physically to this one. So he feels, and this robot will mirror the forces experienced by this one, right? It will render the forces with its joint. So he feels exactly as if he was standing here holding the slave robot and moving it around, and he sees what he would see from that. So it's quite interesting telepresence. And then we've looked at sort of automating various aspects of disassembly. We have quite a lot of work on 3D computer vision and 2D computer vision. We can recognize various different batteries and battery components, a bit like the previous speaker. We also have ways to search for different objects in cluttered heaps. And we can search for an object that's different from our model, but of a similar type as well. So we're trying to keep always thinking about this ability to generalize. So that feeds into quite a lot of work on autonomous grasping. And we're quite proud of this. We think this is probably the most robust autonomous grasping method out there at the moment. It's fully generalizable, doesn't need any prior knowledge of these objects, just captures some point clouds and it searches for the grasps, and is very, very high speed. And we don't use, unlike most of the robotics literature on this, we don't use neural nets or machine learning. We solve it as a geometry problem of matching bits of hand shape to bits of surface shape, which makes it fully generalizable. The trick is how to do that mathematically very fast. We've also done quite a lot of work on cutting, and we were lucky enough to get use of the laser cutting test bed at National Nuclear Lab to try this out. And the robot picks up a camera and it builds up a 3D model in real time of this object. It could be any shape. You can make 2 mouse clicks where you want to start and stop the cut, and the path will be autonomously planned. And then you can show the virtual robot making the virtual cut first, and then the human can say, yeah, go ahead, that looks safe, go ahead and do the real one. Yeah, so that's what I would call human supervised autonomy, perhaps. Yeah. And various experiments to see, can we undo some nuts and bolts, and can we pick up various bits out of these packs? I don't think we've solved it in such a comprehensive way as the previous speaker. I would say we've tried to be a bit more generalizable, a bit less constrained, and the result is bits of techniques at slightly lower TRL, if I was going to compare our work to the previous speaker. So I think the previous speaker got a very good balance between the vision and smart stuff and making something very practical. And starting to look at ways to handle uncertainty. So tactile exploration to find, using the torque sensor of the robot to feel exactly where the bolt is and home in on the screw axis and things like that, and some bimanual operations here. And getting a bit more advanced, this is a bit more recent work where we have 2 robots with 2 different end effector tools and a series of different tasks that need to be performed. And the system is automatically computing an optimal schedule to divide the task between the 2 different robots. And then we have some real-time collision detection and avoidance. So you can see one robot moving out of the way of the other robot, you know, to let each other go past and do these tasks. So it's quite interesting. All of this is fully autonomous, what you're seeing here. And you can see the 2 robots behaving in quite interesting ways towards each other. And then more recent work, which I don't have a video of, is attached that now to a large language model so that humans can type in natural language instructions. You know, a human who has no knowledge of robotics at all, but maybe they know what to do in a dismantling plant and can say, remove all the parts, or remove only the cable, or pick up the module, and the AI will compare what the human says with the vision system, what it's seeing, and look for consistency, and then it will make a plan. And for example, if object A is sitting on top of object B, you can't pick up object B until you picked up object A. So this kind of reasoning we're starting to handle with these recent language models and visual language models that are being bolted onto this kind of planning that you're seeing here. And some work on this is almost traditional direct teleoperation, except that the forces, the haptic forces, are being rendered. You can see using Ali's here using one robot arm as a slave, as a master for the other robot arm, and over here, someone using a very different kind of haptic device that gets finer control to control this cutting work here. And we've had some work looking at how to make the robot automatically adapt the cutting to different materials and surfaces. So if you've got an unknown object coming in, the robot will feel the thickness and the stickiness and the stiffness and the hardness of the material, and it will adapt its depth of cut, its cutting force, its feed rate, and these things online. And this is somewhere halfway between teleoperation and autonomy. It's what I would call shared control. So Max is teleoperating this arm, and the red virtual hand shows wherever the real one is. And as Max is moving this virtual hand over the scene, wherever he goes, the green virtual hand is the AI saying, I can get a good grasp here for you if you like, or a good grasp here. And then he can select one of those, and now the AI will plan the whole reach to grasp trajectory, right? But that's planned autonomously, but Max can retain control. He can control onto the grasp or away from the grasp, right? But he'll get haptic forces that only lets him go the right way. So if you see where my mouse cursor is, if he pulls away left or right, he'll feel springy forces pulling him back onto the right path there, right? So it's somehow the human and the AI in real time collaborating to control this. It's a bit like if you have a car that does automatic reverse parking, and the computer might do the difficult part of turning the steering wheel just right to get you in the tight parking space, but you could have your foot on the gas for stop and go. So you retain that sense. And we've noticed, we've done a lot of work with nuclear industry, and they quite like this kind of human in the loop. And these batteries are similarly hazardous because they're potentially explosive, of course, you know. I'll try to just go on, skip on rapidly.
Yeah, we have to watch out the time a little bit.
Yeah, yeah, I'm nearly done. I don't know why this is not moving. Sorry. Oh, hang on. I think I've crashed.
Yeah, maybe you can explain it in your own words. What you
Yeah,
wanted to show.
just the last thing I was going to show was we've built, if I can, we've built a full-scale heavy-duty robot test bed as well, with big full-size
Packs.
KR500 robots, right?
Oh, okay. Oh no, I see something. Yeah.
Is that working now? Okay. Yeah, Ali also did a bit of work on neural networks for state of health measurement, which is not really our main work, but he's made some papers on this on the side, which are quite interesting to assess this quite rapidly. And this is our heavy-duty robot rig.
I see, yeah.
And because these packs weigh 500 kilos maybe, but these robots, they're not designed for this researchy kind of behaviors. So we had to do quite some work to build the software infrastructure to talk to them. And this is a fairly simple demo. This is not using the smart stuff. It's kind of just pre-programmed to show the physical capability. And in the remainder of the project, we'll be trying to migrate some of these more advanced autonomous methods from the small lab robots onto these bigger ones. But it's quite challenging because of the safety and the scale of them. So I'll stop there.
Yeah, thank you.
We sort of lifted the lid off and done some simple things like that. Yeah, but
yeah, this was also really impressive, and I think it shows already that it's getting complex whenever there is a variation, right? And I understand that we see the history of batteries that have been built, and once we understand one, you can imagine that you understand the whole series of a product, but you can never trust if the next battery really is meets to 100% the previous type of product in the same series, because sometimes things get changed in the production life cycle. And I see there was one question that I missed, maybe, that was addressing, I think, Tomi's presentation, but it was asking, I think Abhishek Parma was asking if there was a reason to use Unity and not Isaac Sim. I'm not sure if you can answer this question.
Yes, so basically, so when we started the project 3 years ago, so Isaac Sim wasn't mature enough, and we had built digital twins in Unity before.
Okay.
So I guess that was the main reason. And also we don't do simulations in the digital twin, so we didn't need Isaac Sim for that either.
Perfect. Okay, I think that answered your question. Yeah, and I think for the next, I mean, we have now, I think we should now go to the next presentation, next topic. And then later in the Q&A, we can address all of these projects that have been presented. I have also some questions, but I think let's wait first. And also thank you, Ali Rida, you were very active in this project, I saw. So it's really appreciated. I think
a lot of this work is Ali, that he's been kind of leading that group of PhD students in the lab who working particularly on the car battery stuff. And it's a body of work that we've been growing since I think we might have been the first people to start on this robot battery theme, or one of the first. And we started from early 2018.
Oh man, yeah, okay.
Looking at this.
I see. Yeah.
And we have certainly not solved it, but we've kind of tried to show robots doing different bits of the tasks, basically, but in quite an adaptive way. Yeah. So.
Yeah, absolutely. There was another question just popping up. Can you mention the frameworks or the architecture of the system? I think that is addressing both of you, right? Tomi and Rustam and Ali Riza. Maybe you can also answer that later in the chat if you like.
Yeah, I think if there's another presentation, I think maybe we should.
Yeah, go ahead with the presentation,
and then we can talk, because we could probably talk about the architecture for an hour or something.
I can imagine, yeah. But maybe you can hint something in the chat, and meanwhile we go to the next one.
Ali can explain the details better than me.
Okay. Yeah, so the next presentation will be about, let me check, the industrial perspectives. So Giampiero and Óscar, go ahead, I think, if you're prepared.
Thank you, Walter. I want to share my screen. Okay.
Perfect. Yeah. Builds up. Perfect. We see it.
Okay, perfect. So thank you, Walter, for your introduction. What does automation really change in battery value chain? So this is the big question. When we look at main challenge in battery recycling, the immediate focus is on replacing manual operation. But that's not the real challenge. We in Comau have seen in our work that the real challenge is scaling automation, when the process itself is complex and non-standardized. Today, automating battery disassembly with standard approach is really hard because the dismantling process of the battery is a process that aren't structured, but so there is a high variability of model to disassemble, because recycling center receive a huge mix of non-homogeneous battery. So we have different geometries, different fasting system, different. Often there is no reliable 3D CAD of the battery. Sometimes different component or the entire battery is damaged or default. So the real issue of this process is the variability, and the variability creates more complexity in the automation, and more complexity means more manual work probably, and manual work means zero scalability. So now you might think this is exactly what robots are for, but the traditional automation has a limitation. It works extremely well when the environment is repeatable, but not work very well in this case because for dismounting the battery we now have fixed reference, no guarantee geometry, no stable condition. So every new battery requires new programming, new validation, new engineering effort. And as I say, the process is not scalable. So how do we solve this? At Comau, we approach the problem on two levels. The first is physical. We design a different system that can absorb variability of the battery, so adaptive gripper or tool changer system, flexible handling. We integrate a 3D vision system that allow the robot to interact with different battery types. But this is not enough because flexibility in hardware does not automatically mean scalability. The really challenge is for us. The real challenge is not only to handle different objects, but the real challenge for us is to adapt the process itself. And this is where we hit the real barrier. That is for us the software. Today, if every new battery requires full reprogramming, the cost of automation grows too fast. So you depend on expert, you increase commissioning time, and you lose the scalability. So the key question is how do we adapt the process without rebuilding it every time? This is where low code changed the game. We as Comau, we are working a lot of to develop some platform for low code programming of the robot that simplify the programming of the robot. So the key point is about changing how we interact with the robot. Instead of programming every detail from scratch, we define the process using a reusable building block. So we have a block for vision system, block for movement, block for unscrewing, handling, etc. So each function becomes a modular skill. The operator doesn't need to rewrite the code from scratch. So we think that this has a direct impact on the value chain because now we can detect the cell faster, the engineering effort decrease, the dependency on expert developers or programmers is reduced, and most importantly, the system can scale across different battery models. So what does automation really change in battery value chain? Yes, it improves efficiency, improves safety, but more than anything, enable the scalability of the process. For us in Comau, this means to move. That means moving from hardware-driven automation to software-driven automation. to see this in action, I'll have you now. I leave now with a video of an industrial application that Comau have done, and in this just a second video. So this is an automatic cell to dismantling a model of battery. In this cell, we use the approach of flexible hardware in dismantling battery, but we are working with a consortium in a reinforced project as part of the battery circular cluster. And in this project, we are taking the next big step, the step that I say, so to develop a really software to low-code programming, to introduce the software-driven approach. Okay, that's all. Thank you for your attention.
Thank you. That was, again, really a next step that we could see here. I see that the machines get better and better, also bigger. It looks like, I mean, a battery can be quite heavy, and I don't know where the trend is at the moment, but 500 kilo is something that often can appear. I'm not sure if there are any questions from the audience right now, because yeah, we have a few minutes for questions left.
As well as the weight, you often need quite a large arm to have the reachability.
Yes,
To
yeah,
find
exactly.
its way around these kind of things. So the robots can get quite big quite quickly, and also some of the tooling could be quite heavy potentially if you need something powerful.
Yeah, makes sense. Yeah.
Yes.
Yeah.
Perfect. Thank you.
Is there anyone in the audience who has a specific question? Unless, if not, then I can go ahead with further questions.
We have a question in the chat. So great presentation. How long does it create to automate the process for a new battery? This is the question for Giampiero.
So your question is how many time needs to create the automation process?
Yes.
In that application that you see, we approximately 1 year, but we need more time to invest in R&D to reach to develop the platform, the software platform to programming the cell.
And we have also one follow-up question. What is the goal with the low-code approach? This is also for you, Giampiero. So yeah, there is a question in the chat.
Okay, we have the main goal is to develop a minimum set of building blocks that can implement very easily to use, I don't know, vision system, handling, and screwing to do this task. We know that these are very challenging goal, because in this process we have different external factor that we need to take in account when we do the really programming and commissioning of the cell. But these are the main. This is the main goal for us. And okay.
Yeah, I mean, we were sort of thinking in a similar direction that you should. Well, I've tended to call it action primitives. So a robot should have the action unscrew, and unscrew should be able to be applied to any screw of any size and type in any location, moving around any type of shape of obstacles, right? And so your vision system can detect object primitives, so screw type X in location Y, and feed it to a screw action robot, do unscrew the screw, right? If that makes sense. Or so if you can encode these actions like screwing, cutting, grasping, moving in ways that are generalizable, then I think what Comau is trying to do is, once you've got those encoded in some way, you can use a relatively small amount of code to say, new battery has come in, first unscrew in XYZ positions, and you can use that powerful generalizable low-level code with a fairly simple small amount of code on top of it. Am I paraphrasing Giampiero correctly?
So to me, this makes
sense. How you're thinking?
Yes, correct. Correct. Is how it is our approach.
What I also think is quite important is, I mean, we always have to keep health and safety in mind with whatever process this is, if it's human being or robot. And I imagine, let's say you pick up something heavy and it falls down. This can be a very critical scenario. And for whatever activity you have already an idea how to process it, I can imagine that there's always in parallel going a check, okay, is this safe? Is there any differentiation? Is there anything that looks different from our standard approach that we have to keep in mind? Is there any impact on health and safety? And I think this is where software can do a lot. Like human beings have an idea of what can go wrong, and this can be mapped with by robots or by software to check, is this really safe? Yeah, I see further questions. Maybe
we can have Óscar's presentation first, and then we can address other questions. Thank you for being very active in the chat.
Yeah, absolutely, makes sense. Go ahead.
Okay, yeah, sure. Let me just start sharing my screen. I mean, it was a pleasure just to be attending like all the presentations, because although we are like in that process, it's like very interesting to see the different approaches that we are following. So let me just introduce. I'm Óscar Palacín from Eurecat Technological Center from Catalonia, located in Cerdanyola del Vallès. And today I will present like very briefly the Battery Burst project that was one of the sister projects of the same Horizon Europe Co, that we are focusing in the next generation on indeed destined to transform the reverse logistic of the electrical vehicle batteries. So let me just introduce the main concept of the whole project. Here you have like the different partners that we are part of the Battery Burst project. The project is coordinated by CEA and also with the other contributions of the partners. And from here you can see like all the flow of the different tasks and solutions that we are developing within the scope of the project. Everything starts with the end of the first life of the battery packs. Then during that process, we are also integrating, as was mentioned before in previous presentations, all the data capture to have like the digital passport of the battery pack, having all the relevant information about the battery, chemistry, the health status, and so on. And then we are just going ahead to the process. It arrives to the workshop. There, my colleagues from Eurecat, from the batteries department, they are developing a tool for performing the first discharging with energy recovery. That's they're working for having like a universal approach. It is also make the state of health assessment and product waste decision in the same process. We also are developing a solution for the safe packaging of the battery packs, because it's a very critical stuff to be in though. And then we arrive to the recycling plant or to the repurposing facility. And here we are developing, in the case of the recycling plant, the semi-automated opening and dismantling of the battery pack that it's taken by us, by the robotics department, and also like the computer vision aided sorting of battery components. And if it's case to repurposing facility, here we are just applying and developing some acoustic diagnosis for knowing the remaining useful life of the modules, and also some machine learning algorithms for the selection of the second life applications. And everything that it's just monitored like a digital twin that takes care of the whole process, and then through simulation optimize all the reverse logistic scenarios. So that's the big picture of the main objective of the project. And now let me just focus like in my part, that it's mostly like in the robotics part. In the case of the different in the dismantling of the battery after opening, it's not complete, sorry, by the title, but basically here from the different tasks that could be automatized during the project, we have selected the unscrewing both of the external and internal part of the battery pack. We have tested it with the Skoda battery packs and also from Nissan Leaf. The one that you can see in the image is a Nissan Leaf battery pack, where we have just modified the cells for 3D printed ones for just doing some tests. So we have like the unscrewing. We are using a collaborative robot because there is a sort of human-robot collaboration in the process. On top, the robot is mounted in a linear axis, basically to add an additional degree of freedom to just reach all the parts of the battery pack. We are using an industrial electric screwdriver, and as you can see, like in the image, it is also equipped with some vision systems. In that case, we are relying in RGB plus depth camera that it's a real sense. There is no doubt that it's a real sense. And then the other task that we are doing is once we unscrew all the screws of the external cover, we are lid removal, like it was presented in previous presentations. We are using that process like an industrial robot. That's not, here we are not using like a smart solution, so we are going with a hard-coded approach. And basically, as you can see, the toolery that we are using, it was completely full designed by us. It has like 4 different vacuum grippers that can be modularly modified just to adapt to the structure and geometry of the lid of the battery pack. And then, as I said, there is some human-robot collaboration that we will see like a short video in the next slide. And we are just working to have like a very agnostic solution. But as I was already presented before, that's the difficulty part of the process. So here we can see small clips of the process of the lid removal and unscrewing. Just additional information, we're considering different types of screws, basically because, for example, from the Nissan Leaf battery pack, there are only hexagonal screws. But when we move to the Skoda pack, they have like several different references. They have a spline, they have Torch one, they have also Phillips one. So the screwdriver that you can see like in the image, it could be interchangeable all the tip of the screwdriver, and then we just can attach different hits to just solve the issues of the screwing with different types. As I was mentioning, let me just a very dummy video about the human-robot collaboration. Basically, in the top right corner, you can see behavior tree. To the ones that don't know what is behavior tree, is basically a library that was originally developed in Eureka, and basically, as it says, you can just program easily in blocks behavior tree. Everything was developed in that case within the robot operating systems framework. And in the video, you can see basically that the robot tries to just release one of the screws. It's just failing for some reasons. Then ask the operator just to release that screw, then it's able to do it. So that's one of the human-robot collaborations that we have, and also we have other ones. I'm moving quickly to the second task that we are developing from the robotics point of view. There is all the part of the sorting for the reuse or recycling of the battery components. Here we are including the second camera, we are using a thermal one, basically because one of the tasks that we want to focus during the project was to do an external inspection of the battery pack, just to check that everything is okay. So with the thermal imagery, it's basically to detect if there is some residual voltage in the battery packs, or there is some thermal anomaly. So we are doing on top of the battery pack like an inspection routine. We're just checking that there is no thermal anomalies at all. Also, as it is said, we have been working like in a generative in-painting pipeline that basically is because we, just to the lack of information and images of some battery packs with defects, we have increases the data sets just to train a model that basically allows us just to detect if there is some anomalies or defects in the battery pack. Then we have integrated a multimodal vision system that relies in both the colored and also all the part of the thermal imagery, and then we can classify the different components of the battery pack. We can do the thermal anomaly inspection, all the detection, and then with all that different outcomes, we have designed an algorithm that basically allows us to classify the battery health status of that battery pack. All that information, it is stated before, it will be included like in the digital battery passport, and it's going to go to the next process. Here you have like a kind of different images. In the top left, you have like some of the different components that we can just classify and segment through the RGB image. On the top right, you have like the alignment of the RGB image and also the thermal one. And here you have like, you can see there is some fake defects that we have generated within painting, and we are able to detect them like in the real images. So basically it's almost everything. We have the last part that we are working like in the Reverse project, because we are almost reaching the end of the project, and indeed the implementation of the robotics part is joining all the different solutions that I before mentioning, like in the integrated prototype for dismantling and sorting. Here you have like the final prototype that we have developed. We have the robotic system, and in the left and right part we have been placed like both battery packs. So that's everything from my side. Thank you. If you have any questions, I will be just pleased for answering them.
Thank you, Óscar. This was, again, a very impressive presentation. I think, yeah, we saw now the topic addressed from different perspectives. And I think, I mean, we are already a little bit over time, but maybe, yeah, first of all, I want to thank you. And for those, I'm not sure, Anastasia, how long we can keep this online going so that people can further stay in the call and yeah, start discussions. Anastasia, do you know how much time do you have that we still can use?
We still have some time. I think it will be great if we can have like a short Q&A session, and as we have lots of questions, so the chat is very active and Q&A section as well. So yeah, probably we can address several questions and pick up several questions and answer them.
That would be great. And yeah, nevertheless, thank you all for giving the presentation. And whoever wants to stay online, please ask your questions, and we will try to answer as many as we can in time. So Anastasia, what is the next one that was, or is there anyone in the audience who wants to ask a question before we go to those that are in the chat? No, I don't think so. So yeah, maybe Anastasia, you can read out the next question that you saw that was not answered yet.
Yes, we have a question. So given the wide variability in battery pack design, what are the biggest challenges for automating dismantling operations? I think this could be addressed by, answered by all the speakers.
Yeah.
So yeah, just.
Who wants to answer this one?
I can actually go on and answer this question. So there are a couple of different challenges we have. One of them is diversity in design of these batteries that all SPKs very well address, and lack of standards in design of such complex products make things, especially actually robotizing the process, more difficult. That's why actually we are trying individually through different projects to create data set of the components, and making such data sets is quite valuable in different ways, not only for vision guided manipulation techniques that we are talking, sometimes integrated with AI driven approaches, but it's important actually to understand that such data sets can help in developing digital passports in order to trace actually these components from mining to the end of life, sometimes to the second life. And in that sense, we can address issues related to, for example, if there is any damage, any sort of deformation at the end of life stage, which is quite important for many different industries, like insurance companies. At least to the best of my knowledge, insurance companies in the UK, they are reluctant to basically collect or even actually doing any sort of repair for such batteries. So in this case, we don't have the option of reuse or repair. That's why actually directly they will send these batteries to salvage centers for shredding, and end of the day we have direct recycle. We have basically a black mass at the end. That there are some debates and arguments about the purity of the material at the end. Some of the material can be recovered and retrieved with a high purity. Some of them are quite difficult. So back to the question. Digital passports from the data set that we are creating is quite important. And when I'm saying digital passport, I'm referring actually to different types of data that we can collect from robotics perspective. 3D CAD models is quite important, but it's not the only parameter. We can collect actually data related to geometry of these batteries, material, color, and various types of parameters. Sorry, it was a long response, but I tried my best to answer two questions at the same time.
But it was a really good answer, and I think, yeah, it was very helpful. The next question, Anastasia, if you can follow up the chat.
Yes, sure. Does the dismantling system described include weight measuring of the dismantled components and waste classification, valorization option for batching different components based on their common recycling characteristics? Whoa, a long question. So it's not specified to whom, for whom this question is. So Dimitar, if you can kindly specify, this will be great. Otherwise, we can ask all our experts to comment on that if that's possible.
Well, I can give you a short answer. So the answer is no. So basically, our system. So we don't weight the components or anything at the moment. Of course, it's possible, but in the current version, we don't do that.
Yeah, I was wondering if every robot has to measure the weight, because he has to understand how far he can extend something before it gets to he can't shift something, for example. So isn't this done automatically anyway with these robots?
No,
Well, it depends on the robot. If you're using a cobot, then it will have some torque sensors at the joints of varying quality depending on the brand, that you can estimate the mass, or you can fit very, very accurate force torque sensors on the wrist, which in principle could weigh these things quite accurately. But generally speaking, you'll just choose a robot that's big enough that you can lift components without worrying it's going to break, so we're not too worried about that. But perhaps there are some useful things that I don't know if the mass can show something useful, but
I think in future it will be in the battery passports that describe the different weight and volume of specific raw materials or components. But this is still a long time to go that is covered in these passports. So I think at the moment, you have to make guesses. in many
Yeah,
cases.
we're more interested in measuring the contact forces for things like controlling cutting, where you've got a forceful interaction between the robot and the object that you're manipulating. Yeah. So there the dynamics gets very complex, and there you want to, maybe you want the robot to behave in a springy, compliant way or something like this, so.
Yes, and as Alberto said, so the battery passport or digital product passports will be more and more important in the future. So once people start using them, so they can include so much information, also for dismantling disassembly, that I guess that'll take some time for sure before it is utilized.
Absolutely. Shall we go to the next question, Anastasia?
Yes. So I will first ask the question from the Q&A section. This is about LLM-based methods. So, and this is for Professor Rustam. You told you have been experimenting with large language models-based methods. So did you also experiment with end-to-end vision language action models? Any particular model you are seeing good results with? And also following this question, there is another one about vision. Since the robot are vision-based, are there any plans to release the data set?
Yeah, so I wrote a bit of an answer in the chat on that. So when we're doing cut path planning or we're doing grass planning, we're just taking a partial point cloud of the scene and looking for a good place to put a hand or searching for a cutting path along it. So we don't actually use any learning there. So there's no training data for something like a 2D YOLO for recognizing different modules. Ali, I think the students were finding lots of images from the internet to train when they.
That's correct. That's correct. Actually, we have used DNN models like YOLO for mainly localization and object detection, and then based on this localization, we are trying actually to manipulate and move the robots to the target position for grasping, etc. But regarding using LLM, VLM models, we have tried actually to develop LLM models in order to enable non-expert users, not necessarily roboticists, to use such frameworks in order to perform difficult or complex scenarios like disassembly. However, there are some challenges involved in terms of number of prompts that you have to train. Computationally, it's very expensive. It's very difficult to perform such process in real time in order to have a closed loop feedback. But we have demonstrated we are able to use large language model in order to create prompts for mainly as a task planner. Let's say if we are using multiple robots, we would like actually to perform a sequence of tasks. Large language model with some challenges worked. However, regarding VLM, this is what we are trying actually to work and develop. But in my opinion, we will have more or less the same challenges. Real-time feedback is one of the main challenges that we have. So the second question was related to release of dataset. In some of our papers, we have released, I'm talking on behalf of Rebellion and the works that we have done at the University of Birmingham. On some of our publications, we have released some data sets for limited number of batteries. However, we have created large data sets for research purposes. We are happy actually to collaborate with other research institutes or universities or industries.
Tomi, you raised a hand on that topic.
Yeah, just a comment for the data sets. So we do plan to publish those in Zenodo. All the data sets that we have created in the project.
Perfect. So any further questions? Anastasia, I hope you
Yes,
keep
yes.
all
Yes, we
so
still
many
have
questions, I
questions.
see.
Yes, we still have questions. So maybe we will limit from maybe two more questions, and then we can close the event. So the question for every speaker: for state of health tests of whole batteries, the BMS is usually blocking the voltage output. How do you check that without opening the battery? How do you check that without opening the battery? Do you have help from the battery builders for this?
Yeah,
Tomi,
Tomi, go ahead.
please go ahead.
Great, thanks. Yeah, so well, Professor Stolkin, you said that we had great results and we'll come maybe further than you, but we have to remember that we have used only one type of battery from Ford. And given that, so as you know, if you want to use the BMS data, we have to have these DBC files. So yes, so the answer is that we have worked with the Ford and they have given us the DBC files so we can actually decrypt the data that is coming through the BMS, through the bus. And in our case, that's how we can do it. And I think there was some other questions related to the same topic. If we can't read the state of health, how does it affect what we do with the battery? So I would say that if we can't determine the state of health, it will be recycled. But it doesn't affect the fact that we can do the robotized dismantling for the batteries. And so the transportation is the same if we can read it or not. So the systems that have been developed for safe transportation, so they have the fire alarm systems, they have a smoke detectors and so on. So they are not relying only on the BMS data that we can read.
Thank you. I think that answers the question quite good. And in general, what I can see from our experience, most companies are really reluctant to share information, even if it's a very outdated model that no one is interested in but the recyclers or maybe some reuse cases, but it's not critical from my point of view, at least, for their actual business in terms of IP let's say in many cases, not in all cases, but in many cases. Of course, there's a lot of hope on the BPP that this will change. But again, there are some limitations in the regulation that say that if there's highly confidential IP or very critical IP affected, then companies still can hold back information. So I assume there will be some partnerships developed over time between specific types of recyclers for specific types of batteries and consortia who then get access to information and others not. And this will then be the differentiator. Especially when you talk about large scale or big volume recycling in very fast procedures, right? Okay, so yeah, maybe one final question, and then as Anastasia said, I think we have to close. But maybe Anastasia, you can later. I'm not sure if Zoom allows this, that we can take a copy of the chat and circulate it to the presenters, to the
Sure.
so
Yes.
that they later can pick that up if they want to answer question.
Yes, we can do that definitely. So if anyone has any other question, this is the right time to ask.
Okay, I think that's it then, right? Okay, so then I think we close now the session. Thank you again for everyone, also for all these questions that have been raised, very interesting ones. There's one thing, Rustam, go ahead.
Gonna make one final comment quickly, which is probably completely obvious, but I'm not sure if anyone specifically said it today, which is this is not going to be solved unless the batteries are designed for disassembly.
Absolutely.
And that probably needs legislation and regulation of some kind. Yeah.
I mean, we have this regulation.
That's my feeling. Yeah.
There is the actual battery regulation, but also the Ecodesign Directive has some clauses stipulating that things need to be or should be designed for getting a more efficient dismantling. Repairability, for example, is something that the European Commission tries to develop concepts and methodologies, how to measure that and how to push that. But it will be something that is already indicated to be data that is included in the passport. So how to dismantle things, how fast it can be, health and safety information to do that, the tools to use for that. We see that, for example, in the PV industry, this is quite common. And health and safety sheets and information for dismantling is something that is, of course, more and more interesting and valuable, especially when you need to have more recycled content in your products. And this again,
we've toured quite a lot of different car factories making the batteries, and they can't even dismantle it themselves.
Exactly, that's the status quo today, right?
If it goes through some manufacturing stages and there's a mistake and they want to strip it back to the previous one, they're hitting it with hammers and crowbars, and
You're right.
These companies, I think they just jumped onto the electric car bandwagon as fast as they could, and they were just trying to get cars out the door, and they hadn't really thought about this, is my impression.
I mean, they want to sell something, right? They don't want to care about reuse, repair, recycling.
Yeah.
But as I said, the regulation is pushing companies in that direction. If they will pick it up or not, this is, I think, will be decided by the market. Also, I think that, of course, there is a conflict of interest, right? For those who want to sell a new product and those who want to take care for the used ones. But there is, we call it, or the regulation has some extended producer responsibilities, which later will be augmented by volumes. So the European Commission and the lawmakers will establish certain volumes of minimum recycled content included, minimum thresholds for repairability expectation, and so on. So yeah, it's going on. Of course it's work in progress. We are at an early stage, and you're absolutely correct. What we see today is it's not designed for reuse, repair, recycling. That's correct. Yeah. Any further final comments? If not, then I think, again, I can only thank you. And Anastasia, also thank you for helping us, for orchestrating this, and for preparing and sharing. If there's any further questions later, I think, you can always reach out to us by email. We can then direct the questions and other comments to the speakers, or you can reach out, of course, directly if you have the contact details. And I think Anastasia will try to make a copy of the questions addressed in this session today and share it.
Yeah, absolutely. And there will also be a recording, so we will publish it on YouTube, and we will share it on our projects pages. So yeah, we will be in touch. And thank you everyone for joining, and thank all the experts who invested their time and joined us and shared their expertise.
Thank you very much for organizing it for us. It's a lot of work, and I appreciate it. Thank you.
Exactly. Thank you.
Thank you very much.
Bye.
Thank you.
Bye.
In contact. Bye. Bye.